So suppose you wanted to create a Taylor polynomial for any old function, but the function you're faced with has as a root a function you've already dealt with. For instance, you know pretty darn well how the sine of x works at this point, I hope. And so here's the sine of x here in black. Wait, I'm on the wrong one. There we are. Here's the sine of x here in red. Here's the first few terms of the Taylor polynomial in blue, and we could certainly add to them to mimic, to approximate that red sine function over even a larger interval. But then here's the infinite Taylor series, well, at least a representation of it using Desmos. We see the green function modeling, mimicking, approximating the red sine function pretty well on the shorter interval that I've provided here. But suppose you wanted now to work on the function sine of x squared. Well, I got good news for you. You don't have to start from scratch. You don't have to start all over and start taking derivatives and derivatives and derivatives and plugging in 0 and blah, blah, blah. You can just build from here. That is, we can compose. Since we had sine of x, and now we have sine of x squared, it's like we're replacing x with x squared. We're composing the function sine of x and the function x squared together. So let's make the composition. Let's replace all of these x's with x squared. Better put some parentheses around that one, huh? Don't worry, I got it. Now that I've got some parentheses, I'll be smart here. Now, I'm not going to go any further than this, but I hope you can see here in blue that the blue polynomial, only 3 terms worth, is modeling, is mimicking, is approximating the sine of x squared function relatively well. And if we continue to add terms, we would continue to get a better approximation. So let's go to the infinite Taylor series and let's replace x with x squared. Like I said, let's just replace x with x squared. There we go. Now watch. Do you believe? How about now? How about now? How you doing? Do you feel good? The more terms we add, the better the approximation. And yes, the green Taylor series approximation does model, does follow, does converge on top of that red sine of x squared function really well. You can do this kind of a thing in a myriad of ways. You've seen it now with sine x over x. Just take sine x and divide everything by x. Sine of x squared. Replace x with x squared. Suppose it was like x times sine of x. You know what? That's actually really fun. Let's do it. What if we had x times sine of x? So we can take, let me go back to where we were. We can just take the Taylor polynomial for sine of x and just multiply by x. Let me rewind it. So in green, you're going to see the Taylor polynomial approximating the red x times sine of x. And as we add more and more terms, there you go. Converges pretty quickly. So yeah, my point is, start with what you know, add on to it, or multiply onto it, or divide onto it, or compose onto it to create what you need. Go do it.